Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I would like to welcome Prasad Kulkarni today. He's a candidate, and he will give a candidate talk on his PhD work at University of Florida.
Florida State University, actually.
Sorry? Florida State University.
Okay, thank you. Thank you for the introduction. So, my name is Prasad Kulkarni. I'm at Florida State. My advisor is Dr. David Wally. And today I will talk to you about some work that I did as part of my dissertation. The title is Exhaustive Phase Order, Search Space Exploration and Evaluation. So for my dissertation, I was working on the phase ordering problem in compilers, which is a well-known and long-standing problem in compiler optimizations, and which was thought to be intractable to solve for a long time. So as part of my dissertation work, I'm happy to say that we have at least satisfactorily addressed it in the context of our compiler, and this is the furthest that anyone has gone with this problem in over 40 years. So I will start off by describing what the phase ordering problem is. So obviously everyone knows the compiler is transforming code from high level to assembly, and along with that, compilers are also used to improve the efficiency of the generated code. So all the compilers use various techniques which are called optimization phases. So now all the optimization phases, they require certain enabling conditions for them to do something. For example, all optimization phases need specific patterns in the code, and by that I mean if you have some optimizations like some loop optimizations, then it is essential that the code have loops, otherwise that optimization won't do anything. Similarly, if you have something like CAC, common sub-expression elimination, then it is essential that the analysis be able to find common sub-expressions for the optimization to do something. Right? At the same time, many optimization phases also need access to available registers. One obvious example is register allocation, which in the absence of free registers, again, won't be able to do anything. So we have observed that optimization phases, they frequently interact with each other by creating and destroying the enabling conditions for other optimization phases. As a result, changing the ordering of applying optimization phases has a potential of producing different code. For example, if you have three optimization phases A, B, and C, then applying them in the order A, B, C as opposed to the order B, C, A can produce different code and which can have different performances. Therefore, in high-performance libraries or for embedded systems, it is an important task to find the best ordering of applying the optimization phases so that the best code can be produced in each case. So then quite simply stated, the phase ordering problem is the problem of finding and ordering of optimization phases which produce the optimal code for every application or every function. However, obviously this problem is very hard, mainly because of two reasons. The first is that current compilers, they contain many different optimization phases, and there are few restrictions on the orderings of those phases. This means that the space of all possible orderings of optimization phases is very large. At the same time, even evaluating the performance of a single phase ordering would require us to compile, link, assemble, execute the program, verify the results to see if they are correct. So this operation of finding the performance of even a single ordering is very expensive. Now, if you want to repeat this operation for many different phase orderings for the entire space, then it becomes very, very expensive. At the same time, it is found that there is no one ordering of phases which will produce the best code for all applications. The best code depends on changes. The best ordering changes by the source application, by the target platform, and also on how the optimization phase is actually implemented in the compiler. As a result, obviously, phase ordering has been a long-standing problem. Yes?
How many phases are typically there?
It changes by compiler. Our compiler has 15 phases. GCC has more. So GCC has a trick actually. So they have some phases which they apply it at different times and have different numbers. So they have something like scheduling 1, scheduling 2, scheduling 3. So they have 15, 20, 30.
And with 15, for example, in your compiler, all 15 factorial permutations are possible.
Yes, I'll get to that. Yes, but yes, that's possible. So that is here. So now I said in my last slide that the space of all possible orderings is very large. So in this slide, I'll just give some numbers to extend that argument. So as I said, in our compiler VPO, we have 15 different optimization phases, and it's possible to reorder them arbitrarily. So that means that there are 15 factorial different orderings of optimization phases. And this is only if we restrict the optimizations to be applicable only once in each ordering. Right? Then we have 15 factorial, which is this large number of orderings which will have to evaluate to find the one best one. However, now as I said, optimization phases can enable each other. So this means that we cannot restrict each optimization phase to be applicable only once in this sequence. They can be applicable any number of times. So if we remove that restriction, we'll actually have to evaluate now 15 raised to 15 possible orderings for each function, which is another large number of the order of 10 raised to 17. But the problem is even harder, because since now phases can enable each other, we cannot even restrict the sequence length to 15. We don't even know what the best sequence length is. It changes by each function for each application. So for our benchmarks, we found that the largest sequence length was of active phases was 44, which for that function gave us a space of something like of the order of 10 raised to 51, which is a really large number of orderings to evaluate, and it's certainly impossible. So obviously, exhaustive phase ordering was considered intractable for a long time. In fact, it was so firmly entrenched in the minds of compiler researchers that exhaustive phase ordering cannot be done that no one had even attempted it in the last 40 years. So based on some of the earlier experiments that I did, I started working on exhaustive phase ordering, and one of the main results of my dissertation was we have now been able to exhaustively evaluate the optimization phase order space for a large number of functions, for most of the functions in our benchmark suite. So this talk will talk about how I was able to do that. Now obviously I gave you those large numbers, and it's certainly not possible to enumerate and exhaustively enumerate and evaluate all possible orderings, all possible 10 raised to 51, 10 raised to 11, 14, 18 different orderings of optimization phases. But one of the important results was that from some of my earlier experiments was that we found that there is a lot of redundancy in the space, in the sense that there are, in many cases, many different orderings of phases that eventually produce the same code. So what that means is that obviously the number of different versions of the function that can be produced by phase ordering is always a subset of the number of different phase orderings. But if there is a lot of redundancy in this space, then the number of possible versions is a very small subset of the number of possible phase orderings. So instead of trying to enumerate all possible phase orderings, if we instead concentrate on only generating the possible different versions of the function, then maybe the problem can be made more manageable. So this was the main intuition I started out with, that don't concentrate on enumerating, evaluating all possible phase orderings. Instead, try to enumerate all possible function instances that can be produced by the different phase orderings, and only concentrate on that, which is a much smaller problem. So that was the intuition, and this is the outline for the remainder of my presentation. And I'll start off by describing our experimental framework. So as I said, for our experiments, we use the VPO compiler framework. VPO stands for Very Portable Optimizer. It's quite a mature optimization framework, which was started development in 1988. Our current performance is comparable to the performance given by GCC, the -O2 option. The nice part about VPO is that it performs all its transformations on a single intermediate language representation, which is called RTLs, and that's why it's possible to have any reordering, to arbitrarily reorder the phases. For our experiments, we use all the 15 reorderable optimization phases that were available in VPO, and we had directed the study for the embedded domain, and so we selected the StrongArm SA100 processor for our for the architecture, and whenever we needed performance measurements, we used the simple scalar simulator toolset. So this table lists the different optimization phases that are present in VPO, and without going into detail about what each of this does, I just wanted to point out that VPO is a compiler backend, and we have in a compiler present most of the optimization phases that are normally present in a typical C compiler backend. At the same time, I do have some disclaimers. The first is that, as I said, VPO is a backend, and so we did not include optimizations that are normally present in the compiler front ends, like memory hierarchy optimizations or inlining and other interprocedural optimizations. At the same time, we were only concerned with the phase ordering problem, and so did not vary how phases are actually applied. So the only case where this is relevant is in the case of loop unrolling. We only applied loop unrolling once for every loop with a loop unroll factor of 2, and did not try out other different loop unrolling factors. At the same time, we also did not include optimizations that needed a specific profiling phase before the optimization, just to keep the study simple. So this is our benchmark suite. I used benchmarks from the MIBench benchmark suite, which is a benchmark suite targeted of C benchmarks targeted for the embedded domain. The benchmarks in MIBench are divided into 6 categories, which are listed here. I selected 2 benchmarks from each of the 6 categories of benchmarks in MIBench, which are here. And the more important thing is that VPO operates on individual functions at a time. And over these 12 benchmarks, there were a total of 244 different functions that we studied. So in the next part, I will describe the approach, the algorithm that we used to get exhaustive phase order evaluation. Before that, I'll just describe some terminology I'll be using for the rest of the presentation. The first is an active phase. So as I mentioned, each optimization phase needs certain enabling conditions for it to do something. So if an optimization phase has those conditions present, then it will obviously go and modify the function. Such phases are called active phases. Now, if an optimization phase is not able to find any opportunity to change the function representation, then that phase is called a dormant phase. I've also formally defined a function instance as any semantically, syntactically, and functionally correct representation of the source program or the source function. This is just, in a sense, a different version of the function that can be produced by a different phase ordering. So now we'll describe the actual algorithm that we go through. So now again, we are concentrating on getting different function instances instead of getting different phase orderings. So we start out by at the unoptimized function instance at the root level. We then apply all the different optimization phases that are present in our compiler to this unoptimized function instance. So although we have 15 different phases in this graph, for illustration purposes, I'm only showing 4 phases. So then we get new function instances at the next level. To get new function instances for each successive level, we again apply all the different optimization phases to all the distinct function instances that were present at the preceding level to get new function instances. So as you can see, this representation, the naive optimization phase order space, is now represented in the form of a tree where nodes are function instances and edges represent transition from one function instance to another on application of an optimization phase. At the same time, you can also see that there is an exponential growth in the number of function instances at every level, and very soon this space will become infeasible or impractical to exhaustively enumerate. Now in the next slide, I will show how we can find redundancy in this space and remove certain nodes, remove certain edges to make this space, to make the growth more manageable at each level. So the first technique to prune this space is eliminating consecutively applied phases. This is really trivial, and is a characteristic of our compiler that each optimization phase can only be active once consecutively. So if you have applied an optimization phase, it disables itself. It cannot be applied again immediately. So for example, if you have applied phase A here, then if you again try to apply A here, it would be dormant. It won't be able to do something because it has already finished everything the first time. So this allows us to not even attempt some phases at the next level. The second technique is eliminating dormant phases. So now again, as I said, each optimization phase needs certain enabling conditions to apply itself. I changed our compiler so that we get feedback from the compiler telling us if the last phase was able to make any changes. If it was not, if it did not make any changes, then the function representation is essentially the same from before, and so there's no need to again add it at the next level. So finding dormant phases allows us to get rid of more function instances from this graph. Now at the same time, it is also possible that two different orderings of optimization phases can still produce the same code. This can happen for 2 reasons. The first is that some optimization phases are inherently independent. For example, if you take something like branch chaining and register allocation, then they work on different sections of the code. They do not share any resources, and so applying them in any order should produce the same code. It is also possible that 2 different sequences or 2 different orderings of different optimization phases can still produce the same code. For example, as you can see here, the code that is produced after instruction selection is the same as the code produced after constant propagation and followed by dead assignment elimination. So if we found such instances where different orderings are producing the same code, then we only need to keep one function instance and remove all the others. Now it is also possible that 2 different function instances are not exactly identical, but they are guaranteed to produce the same performance. So in our case, what we measured was 2 instances which are not identical, but the only differences are the register numbers that are assigned or the labels of the basic blocks that are used. So in this case, we can see that these 2 different code instances are essentially the same. The only difference are the register numbers and the labels of the basic blocks. We can remap these to a different function instance by just remapping the registers and the basic block numbers, and this allows us to find more instances when the functions are not identical but are essentially equivalent. So in such cases, we only need to keep one function instance and we can remove all the others. So obviously this has to be done carefully, because even after removing the dormant phases, there are still tens of thousands of different function instances present. So if we want to if we want to find identical or equivalent function instances, we essentially have to compare each function instance with all previous function instances to find if they are identical, right? So this, if we have to do this check naively, then we have to keep all the previous function instances in memory, which is too expensive in space. At the same time, if we do a bitewise comparison of the current function instance with all the previous ones, it will also be too time consuming. We therefore used CRC checksums on the bytes of the RTLs and only compare the CRC checksums of the current function with the CRC checksums of all the previous function instances to check for a match, to check for identical function instances. We also used multi-level hash tables to make the searches more efficient. So now the result of finding or eliminating identical and equivalent function instances is essentially converting the tree into a DAG, as we can see here. So at the same time, what is important is that there is no longer an exponential growth in the search space at each level, and which is what we had expected and which is what we see in most of the functions that we study. So this allowed us to exhaustively enumerate the phase order space for a large bunch of functions. So as I said, we started out with 244 different functions. The exhaustive enumeration for most of these functions typically only required a few seconds or a few minutes. Some of the larger ones required a few hours or even a couple of days. But now there were some functions which had phase order spaces just too large to enumerate in a reasonable amount of time, which was in our case a span of 5 to 7 days. So if you're not able to exhaustively enumerate after that time, then we did not pursue those functions further. So out of the 244 functions, we were able to exhaustively enumerate 234 of these functions in a reasonable amount of time. So this table shows the static enumeration results only over those 234 functions. So the first column lists the different functions that we have. The second column gives the number of assembly line instructions in the unoptimized version of the function. So as you can see, some of these functions are very large, they're not very small functions. The next column gives the number of distinct function instances, different versions of the function that we found for each function. This is essentially the number of nodes in the DAG. The next column gives the length, which is essentially the depth in the DAG, the length of the largest active sequence of optimization phases for that function. The next column is important as I'll be using it for a further study. It is the number of distinct control flows for each function. So I will describe it in more detail when I describe that part of my talk. But essentially, it's important to realize that this is a very small number. The number of distinct control flows of the basic blocks is a very small number as compared to the number of distinct function instances, which is understandable because many different phases like register allocation or even CAC, they don't generally change the control flow of the function, but only change the instructions within each basic block. The last column compares the size of the function that is produced by a default compilation sequence as compared to the optimal phase ordering code size. So even though a compiler was So a VPO compiler is a very aggressive compiler. It does optimizations in the same order, but it repeats them in a loop so that so there is no optimization phase can be applied after the default sequence. So it applies the optimizations in a loop till no further optimizations can be applied. So even after such an aggressive compiler, on average, the code produced by VPO was 6.46% worse in code size as compared to the optimal phase ordering. In the worst case, it was more than 33% worse. Yes?
Is the average, like in the length, it seems like smaller than all the numbers?
Oh, this one?
For the length.
Oh yeah, but this is the average over 234 different functions. And I've only listed some of the part of the table here. So yeah, this is the average over all the 234 functions. Yes?
So the last column, was that percent or was that an absolute number?
This is a percent.
Is it six-fold slower or
No, it's 6.46% slower, yes, on average. In the worst case, the worst function was 60. It's not slower, it's just the code size, so it's smaller. So it's the worst case was 67% or 68% larger, the default compiler.
So can you go back one second?
Yes.
So this is the 6.46 is on an average. The most optimal function was 6.46 times 6.46% larger.
Yes,
than the original function.
Okay, so this is the code size of the function that is produced after compiling it with our default compilation sequence and comparing with the best phase ordering function instance. So the code that is produced by a default compiler is 6.46% larger than the code that is the the best phase ordering, the smallest code.
So is the size of the code the notion of optimality?
In this case it is. Yeah, in this case it is just the code size. We haven't done any dynamic measures at this point. So this is just the code size, and the code size is 6% worse. So the functions produced by a default compiler are larger.
So I'm not that familiar with compiler. You said it's 6.46% improvement.
In terms of bytes.
Is that a big deal in compiler research?
This is on average, you see. Yes, and in some applications for embedded systems or for high performance libraries, it's important. Especially for embedded systems, what happens is you want to reduce the code size as much as possible, so you can fit your application in smaller number of chips.
Sure.
And if you can just reduce one chip, then you can, over 1 million units, you can save a lot of.
What was the best case for your experiments?
Like 68% of.
68%.
Yes. So some of the smaller functions, they were like 0, right? Because there was the batch compiler was able to produce the optimal code sequence. So this gave us the first important result that we have, was that we are now able to exhaustively enumerate the optimization phase order space to find an optimal phase ordering with respect to code size for most of the functions in our benchmark suite. So this had never been done before, and this is still a very important result for the same thing I said, that code size is a first-class design constraint in embedded systems for which we are targeting. And this result is published in our CGO paper in 2006. Now we have the best phase ordering function instance for optimal code size, but we still want to find the best function instance for some dynamic performance measures like cycles or time or something. So yes.
So is the purpose of this that if I have a piece of code that I'm really interested in, that I will run the exhaustive search on that code, or is it that you will come up with one ordering that's very good for a compiler in general?
So it's actually both. In this talk, I'll mostly concentrate on the first part. That is, you're given a function and you have to run this algorithm on that function to find the best phase ordering. So after doing this, when you have the data of the entire space for many functions, then you can actually find the interactions that are going on in the compiler optimizations. And then you can maybe come up with a sequence which is good. But the second part is there is no one sequence, as I said before, which will produce the best code for all functions. In a later study, I have not published that as yet, but I found out that the best performance in terms of cycles that can be produced by our compiler with a single optimization sequence, any sequence, it's a single sequence over all the functions, is 4.4% worse than the optimal phase ordering. So a single sequence will never be optimal for all the functions. Okay, so now the next part is we want to find the best phase ordering with respect to some dynamic performance measure like cycles or time. However, that problem is even more difficult to do. So here this is a minor point. Just be with me. This is slightly confusing. So as I said, I started out with 244 different functions, and I've been able to exhaustively evaluate or enumerate the phase order space for 234 out of those 244 functions. However, with the input data set that was provided with MIBench, I was only able to execute 79 of those 234 functions. So when we come here to determine the dynamic performance, I'm only considering the 79 functions which were actually executed with the input data set provided with MIBench. So over those 79 functions, we had over 175,000 distinct function instances on average. Now, if you want to find the best dynamically performing function instance, then you have to either execute or simulate each of those function instances for all functions. Now, this is really expensive to do because finding the dynamic performance would require us to assemble, link, and execute the application, which is typically more expensive than just compiling. At the same time, we are targeting this for an embedded environment, and many embedded systems don't have a runtime environment on the infrastructure. So they use simulations, which is again orders of magnitude more expensive than native execution. Therefore, it was very important for us to reduce the number of executions, but still find the best phase ordering with respect to dynamic performance. So we have to use estimation, but the estimation has to be sufficiently accurate. So we used a very basic notion in compilers, which is well known, is that different function instances of the same function having identical control flow graphs will execute each block the same number of times. So I'll show an example of this in my next slide, but it's understandable. If you have the same control flow, the basic blocks, the same function, then the same input data will instrument the same basic blocks. So
it depends on it depends on the predicates controlling. It depends on the instructions at each place and the predicates at each branch point, right?
But it's the same input data.
It's the same input data, so it's still instrumenting the same part of the code.
But his point is that if the branches are different, then the control flow could, in practice at runtime, could be different. So the question is, when you say identical control flow graph, what do you mean by identical control flow graph?
I was just assuming that you're just looking at how the PCs are connected and you're completely throwing away the instructions and
we are still
predicates guarding each if then else.
No, we are still comparing the branch instructions and the branch control statements. So we know where each branch is going. And if the branch instruction is different, if they are comparing different, if they have different signs or different offsets, then they are different blocks, they're different control flows.
Ah, okay. But you're ignoring the statements.
Yes, of course, yes.
Okay. So, I mean, that's still not perfectly accurate, but it's better than...
This is still an estimation.
Okay, sure.
So this is of course an estimation.
Of course. Okay, good.
So equivalence of control flow graph, is that graph equivalence?
What's that?
So when you compare control flow graphs, are you doing graph equivalence, or are you saying, okay, this is the sequence of basic blocks and they have to be exactly the same, they set the same sequence and everything?
Yeah, they have to be exactly the same. So they have to branch to the same. So I normalize it, the set of basic blocks in terms of the branch conditions and which block is branching to which blocks. And then it's a direct comparison between two different control flows.
So, Bjarne, I think the problem is equivalent to graph isomorphism with
Right.
labeled edges, which can be done polynomially.
With what?
With labeled edges.
Right, but in this case, I mean, some machines, different jumps forward or jump backwards have different costs.
Okay. Well, that's
Okay, that is still an estimation problem, right?
Right.
This
That's why I
is-
asked if you took your basic blocks and listed them in order and actually provided an order and just
Yes, we are-
that comparison, or whether you did graph isomorphism.
No, I did not do anything very complicated, so I did not use graph isomorphism. I just use, so it was just trying to see which block is branching to which other blocks, and if it's still branching to the same blocks in the second control flow.
Okay.
So the algorithm basically proceeds as follows: that we use the phase ordering to generate a new function instance, and then we check to see if the control flow of that function instance is similar to some other control flow which we had seen earlier. And if it is not, then we have to go ahead and execute the application for that control flow. Then we can at the same time statically estimate the number of cycles required to execute each basic block. That depends on the instructions in that basic block. So we will statically estimate the number of instructions. And here we can take into consideration stalls due to data hazards, but we do not consider other things like branch misprediction or cache effects and everything. So finally, the dynamic frequency measure as defined by us is just a sum of the number of static cycles for each block times the block frequency, the execution block frequency of all the blocks. So let me show that here graphically. So this is an instance of a control flow as we describe it. These are just the basic blocks, and we can statically estimate the number of cycles required to execute each basic block. So now if this is the first time we are seeing this control flow, then we have to execute the application. After execution, we now have before execution, we also instrument the function to find the number of times, to count the number of times each basic block is executed. So after execution, we now have the basic block counts. And so the total cycles is just a summation of the products of the number of cycles times the number of times a block was executed. Now further down, if we find another function instance which has the same control flow graph, then we can again statically determine the number of cycles. But we don't have to execute this function instance again, because we can just get the cycles, the basic block cycles, from the previous control flow instance, and we can directly calculate the number of cycles. So this saves us some simulation for each. So we are not simulating the application for each function instance, but only simulating it once for the set of function instances having similar control flow graphs. So now, since the number of different control flow graphs was much smaller than the number of different function instances, this is a big win in practice. Yes.
This works for something simple like the ARM, but do you think it would work for the x86 with an out-of-order execution and all the sort of tricks they play?
Yes, it would be, the estimate might not be that accurate. But here, as I will describe further also, that we are making the estimation problem much simpler. So now it's much difficult to, we are only trying to find the relatively superior function instance between two instances which have the same control flow. So this is actually a much simpler estimation problem to solve than trying to find which function instance is better when they are not related in any manner. At the same time, the estimation is not as accurate if you move to some out of order pipeline and some machine like x86. But then you can have some, so the estimation problem can then be reduced to, it's still an estimation problem. So you will have to have better models, better cache models, better pipeline models, and you do a better estimation job.
Why is it better than just run, getting the exact answer off of a particular processor by running it using cycle counters?
Because it's difficult to do. Because it's very time consuming. As I said, we have over 175,000 different function instances for each function. So executing those many times,
How long do they execute for?
that depends on the application, but some applications, so this was actually simulation because it didn't have an actual ARM. So we were simulating it on an x86 processor using simple scalar. So some of the simulations require us, cycle level simulators would take each execution or each simulation will require us half an hour, 10 minutes, 20 minutes, 5 minutes. So it's really expensive to do. Even execution is very expensive, right? Even if you consider the execution takes like 5 seconds, if you have to do it for 175,000 times, it is still a significant amount of time to spend for each function. Okay, so these are our, okay, yes.
How accurate is your estimation compared to the simulation?
I'll come to that.
Okay.
I have that in my later slides. So this is the dynamic frequency results table. Most of the columns are still similar from what the static table was. So I'll just describe the ones which are different. So obviously this is only over the 79 executed functions in MI bench. The number of different function instances is close to 175,000 on average. At the same time, the number of different control flows is only 47. So this means that we have to execute or simulate the application only 47 times instead of 175,000 times. The next column shows leaf function instances. So leaf instances are those on which no additional optimization phase is able to make any changes to the function. So these are essentially the leaf nodes in that DAG. So this is again important because I use it in a further study. But just important to realize that there are fewer leaves obviously than the number of different function instances. The last two columns compare the performance of our default compiler sequence with the optimal function instance as defined by our dynamic frequency measures. The batch compiler is 4.8% worse than the optimal phase ordering sequence. The last column compare the performance of the worst leaf compared to the best phase ordering. The worst leaf is 65.4% worse than the optimal. And we are comparing leaves because we just want to show that our compiler VPO is highly optimized over all these 20 years or 19 years. And that's why we have found an ordering which is already very good. If the compiler was not optimized to fight for performance for all these years, then this is how much worse it can be. This is still a leaf sequence, but on average it can be so much worse. So now, as you all mentioned, that our measurements are still based on estimations, and estimations are known to be inaccurate. So the estimations, we have certainly ignored cache and branch misprediction effects. But we still believe that our dynamic frequency counts may be sufficiently accurate for our purposes, and this is mainly because of two reasons. One of which I already mentioned, that we have greatly simplified the estimation problem by only trying to find the superior function instance between two instances having the same control flow. And most embedded systems like the ARM have simpler architectures like simpler pipelines, simpler memory hierarchy structures, and so estimation should be reasonably accurate. However, we want to verify how good it is as compared to simulator cycles. And therefore, in the next set of experiments, we try to show that we have actually a strong correlation between our measure of performance and simulator cycles. So this is one graph over one typical function, which is init search in string search, which actually compares the simulator cycles as compared to our measure of frequency counts or all the different function instances for this function. Now, two important things to notice here is that the two lines are pretty well correlated. However, it's less important that they are actually the same, because we are only interested in finding the best function instance, and we are not interested or finding the accurate performance. It's just finding the best instance, so which we are able to do. At the same time, another point to notice is that the correlation actually gets very good as the function is better optimized. And this is the region of interest, and this is where the best function instance will reside. So a better correlation along this point is more interesting. At the same time, we can also see that this is a very small function. It only has about 1400 instances, when on average I said that there were over 175,000 different instances. So we are able to do this for this function. However, if we have to again do it over all the 79 functions, it would again take us very long. We therefore decided to restrict our study to only leaf function instances. So now, as I mentioned earlier, leaf instances are those that are generated when no additional phases can be successfully applied. So why leaf instances? We selected to do this study over leaf instances because we thought that leaf instances will provide us a good sampling. Mainly because our compiler VPO, it can only generate leaf function instances because it applies optimizations in a loop till there are no further changes. And therefore, it was important to us to see what is the best leaf performing function instance. At the same time, leaf instances generally give us good performance. This is understandable because leaf instances are generated when you already applied a bunch of optimization phases. And optimizations are typically geared to improve performance, and so applying more of them should give us better performance. We found that for over 86% of the functions, there was at least one leaf function instance which was optimal. At the same time, there was also a significant percentage of leaf function instances among the total number of optimal function instances. Even when the leaf function instance was not the optimal, it was typically very close to the optimal function instance. And so we decided to restrict the correlation study to only leaf instances. So we used two different correlation metrics. The first is Pearson's correlation coefficient, which is a standard correlation metric in such correlation studies. The second is measure of correlation was something we defined ourselves, which is just a ratio of the cycle count for the best leaf divided by the cycle count of the leaf with the best dynamic frequency measure. So here this is, so the best cycle count is always one. There's only one best cycle count, but there can be more than one leaf which we estimate to be the best, in which case we have to simulate all the leaves which we estimate to be the best. So this basically shows how close our estimates were to the simulator estimates or the simulator cycles. So this table gives us a leaf function correlation statistics. The Pearson's correlation coefficient of 0.96 shows that there is excellent correlation between our measure of our estimations and simulator cycles. The next two columns, next two pairs of columns gives the L-core ratio, which is a ratio of the best cycle counts to the best estimation that we did. So here we can, so the first is when we only consider function instances which we estimated to be the best. And in the next pair of columns, we consider all function instances which were within 1% of our estimated best. So in this case, we have to simulate fewer instances. So this mainly shows that if we only simulate 4.38% of our best estimated function instances, then we can get within 98% of optimal. At the same time, if we increase the number of simulations and we only simulate 21 instances which we estimated to be the best, then we can get within 99.6% of optimal. So here we wanted to show that we can still enumerate the space, use our static estimations, and then we can only find a small subset of functions which we later then have to simulate to get very close to optimal, within 99.6% of optimal. So this was my second result, that we have now been able to exhaustively evaluate the optimization phase order space to find an optimal phase ordering with respect to our estimation of performance, and also find a near optimal phase ordering with respect to simulator cycles. So this result was published in our LCTS paper in 2006. Okay, so now we have exhaustively enumerated this large space, and we have the phase ordering space for a large number of functions. So what we can do, we can analyze that space and use it to improve the default compiler. So that was the next part, how we can find the interactions of optimization phases and how we can use them to make the default compilation better. So in this case, I have used it to make a conventional compilation faster. So this was some work that was published in CGO as well, and I'll describe it in my further slides. So for this, I basically found out two different interactions between optimization phases. The first is the phase enabling interaction, which you can see along this path quite easily. So as I said, after applying optimization phase A, it is dormant at this point. But now after application of B, we can see that A is again applied, is again active. So this means that along this path, the phase B has enabled phase A. So although B is able to enable phase A along one path, it's not the case that B enables A along all paths. So you can see along this path, after application of B, A has not been enabled. So this enabling of one phase by some other phase is a probability of how many times it can do it on how many different control flows. And therefore we define the probability table of each phase enabling each of the other phases. So all these characters denote optimization phases, 15 phases here and 15 columns and rows. The second column is the probability of a phase being active at the start of the optimization process for the unoptimized function instance. There are many columns here which are blank, for which we are not able to detect any enabling interaction between that pair of phases. Most of these numbers are very low. One prominent interaction was between register allocation, which is denoted by K. It frequently enabled both common subexpression elimination and instruction selection, which is denoted by S.
So how did you compute these probabilities?
So these are essentially just the. So along for each function, this is average over all the 234 functions. So for each function, we just calculate how many times that phase is actually enabling some other phase immediately in the very next level. So they're just one level interactions. So we are not considering any multi-level interactions.
So it's an empirical measurement over all.
Yes, it's an empirical over all the measurements, yeah. So the second complementary interaction is the phase disabling interaction, where some phase disables some other phase which was active previously. So this can be seen here. Like at the root node, optimization phase A is active, but after applying B, A is no longer active. So along this path, B has actually disabled A. So again, the disabling probability is also a probability of some phase disabling some other phase along some of the paths, but not along all the paths. And so we can come up with a similar disabling probability table. So again, most of the values here are very small, and many columns are empty because in our compiler, these interactions don't typically happen very often. And this is also one of the reasons why we were able to exhaustively enumerate the space, just because the enabling and disabling interaction numbers are typically so low. One prominent thing is obviously along the diagonal, everything is 1 because each phase in our compiler disables itself.
So I just want to ask again to make sure I'm clear on this. What you did is you ran one phase, and then you ran another phase after it, and all you saw was whether anything happened. I guess I'm unclear what you mean by enabling or disabling.
Okay.
So you ran one phase, and then you saw if the next phase actually did any additional work, but
Right. Okay. So
it still doesn't seem, it's not precise enough.
Okay. So we have our entire phase order space graph in the form of the DAG that I showed earlier.
Yeah.
Right. For each function instance, we know that. So for some particular function instance, there were 3 different edges from that node, say A, B, and C. Right. So for that function instance, there were A, B, and C. These 3 phases were active. So after applying B, if you go down, maybe there is no edge from that point for A. So although A was, so as you can see here, right, A is active here, but so this is enabling. So A is active here. So for this function instance, A is no longer active because each phase can only be active once consecutively. So it's dormant for this function instance. But after applying B, A has again been active. So there's something that B did to this function instance before getting to this instance that A is again active again. Right. So that is the main enabling interaction. That it is something that B did that enabled A. Otherwise, there is no chance for A to be active again.
Okay.
So this is just a single level interaction. There could be multiple things, right? There could be like B, C, D is enabling A. But in our case, we would only consider the last phase as enabling the phase after it. Okay, so now we use these enabling and disabling interactions to actually improve our conventional compiler, to make it faster. So the basic intuition was that, as I said, our compiler VPO is a very aggressive compiler. It was applying optimizations in a loop. So that means that many times when VPO applied a phase, that phase was dormant at that point. So here we thought that if we could use the enabling and disabling probabilities to find the active phases then we can eliminate some of the dormant phases from even being applied, and by that we can speed up our conventional compiler. So that was the main intuition, and I'll go over the algorithm that we used. So in this case, Pi is the current probability of the phase I being active, and Eij is the probability of the phase j enabling phase I, Dij is the probability of phase j disabling phase I. So for each phase, the initial probability of that phase being active is the probability of that phase being enabled for the unoptimized function instance at the start of the optimization process. Then in each pass of this while loop, we select the phase which has the highest chance of being active, and we select that phase and apply it. So if that phase is actually active and is able to make any change, then we change the active probabilities of all the other phases by the probability of that phase enabling all the other phases and the probability of that phase disabling all the other phases. And we again repeat this loop till any phase has an active probability ratio. Yes?
So in the original VPO, you had one last iteration of the loop where nothing was done, right?
Yes.
So that was kind of like proof that there could be nothing more done.
Mm-hmm.
Now, in your environment, you could have multiple phases enabling another phase.
Mm-hmm.
But if your phase probability graph doesn't show that, then all the probabilities will be zero, even though there is still work possible.
Yes, yeah. So this mainly depends on, it's possible that it's certainly possible that given the tables we have, the empirical results we have, because we are not considering, when we do this, when we consider probabilities, we are not considering the probabilities for the current function. So in each case, we only consider the tables for 233 functions, and we try to optimize the 234th function. So then it's possible that some interaction is not captured, and we might not actually generate a leaf in each case. Yes.
So you thought about just adding after you loop?
We can do that. Yes. Yeah. We can just apply all the phases again, or we can just run our compiler again. Yes. But here the main thing was making the compiler faster. So we wanted to reduce the number of phases that could be applied. So this compares the old compilation with our new probabilistic compiler. So as I said, in the old compiler, there were a lot of phases which were attempted. Many of them were dormant, so a very few of them were actually active. In the probability table, in our new compiler, in a probabilistic compiler, we actually reduced the number of attempted phases by still maintaining the number of phases which are actually active. And this is reflected here in the sense that the time for the compiler, the time taken by the compiler to compile the application is reduced by over 70%. So it only takes less than 0.3% of the time, or 30% of the time it required earlier. And we have still maintained comparable performance.
So the compiler is 3 times faster.
The compiler is over 70 times faster.
Yeah, over 3 times faster.
Yes, okay.
So if I understand correctly, what you're doing essentially is generating this disabling and enabling probabilities based on your inputs, which are the functions, right?
Yes.
So how does this method depend on how representative the functions are? Let's say I give a very different function.
Mm-hmm. So this is essentially based on the representation of the phase order space. So if you have, so this is after we have enumerated the entire space. So if we have the entire space present, then finding the interactions is trivial in the way we have defined them. And once we have the interactions, we can get the tables.
Yeah. But what if I give it a totally different function, different application?
Mm-hmm.
How will your compiler perform compared to?
You mean the probabilistic compiler?
Yeah, the probabilistic compiler.
Well, that's what I said, that even the tables that we used, for each function that we were studying, we didn't consider the probabilities of that function in the table. So we have a total of 234 functions, and before starting each function, we only used 233 of the remaining functions to get the tables, and use those probabilities for the last function.
Okay.
So yes. So finally, the conclusions. So I was studying the phase ordering problem, which has been a long-standing problem in compiler optimizations, and for which exhaustive evaluation was always considered impractical or impossible to do. As part of my dissertation, I've shown that it is possible to exhaustively evaluate the phase order space for most of the functions, at least in our benchmark suite and for our compiler. And this was made possible by providing a reinterpretation of the problem of instead concentrating on enumerating all the possible orderings. You instead concentrate on all the possible function instances. We also developed novel algorithms or novel search algorithms to explore the space. along with fast pruning techniques and accurate estimation methods in order to get here. Yes.
So one key assumption over here is that the same phase cannot be applied immediately after it's applied, right?
That's not really an assumption. That is something that is true in our compiler.
But you could think of something like inlining.
Oh yes, okay. That can happen. So we have. So
then you could have, A's in that phase order space, and
yes, you can have that. So we didn't have inlining, and the other thing is that is even possible for something like loop unrolling. You can go on unrolling any number of times. So in that case, we restricted such optimizations to be only applicable once in that ordering.
But even if you have one optimization, say A, which can be multiply applied.
Okay, then we do it in a loop. So
but my point is that the phase order space can immediately grow very large, even if you have just one optimization thing that can be multiply applied.
If there is one optimization which can be applied more than once consecutively, you are saying?
Yes.
Yes. So in our compiler, what is done is each optimization phase is applied in a loop till it finds everything that it can. And we had to restrict. I think the only thing we had to restrict was loop unrolling, because loop unrolling you can. So for loop unrolling, you can only unroll each loop once, and with a factor of 2. Okay. So also I analyzed some properties of the phase order space. In this case, I have shown how we can use them to speed up our conventional compiler. And these results are published in our CGO, LCTS, and have been submitted to TOPLUS. So some challenges briefly. So obviously every one of you, I guess many of you have worked in compilers, and you realize that it's difficult even with the default compiler with one ordering to produce correct code for many different benchmarks. Now if you start reordering the optimization, then then producing correct code becomes very, very hard. It's a severe stress test for the compiler. Like the first 1.5 years, I just had to debug the compiler, which was perfectly fine for the default ordering that it had. But once I start reordering the phases, it starts producing incorrect code because many assumptions that are made for one particular phase are no longer true. So at the same time, we also wanted to make our study very efficient. And so we had to isolate the analysis that is required before each phase. So after each phase, we cannot invalidate all the analysis, all the data flow, all the control for analysis. But we only invalidate and reapply the analysis which can be disabled by the previous phase. So the second point is obviously we have to produce correct code for all possible phase orderings. At the same time, this entire algorithm runs in memory over several hours, over several days. And so it's important to eliminate all memory leaks. There were some memory leaks in a compiler which were very small, but we could never see them because they were operating on a single file for a couple of seconds. But once you start doing this, it's very important to get rid of all the memory leaks. At the same time, the search algorithm has to be made highly efficient. So I already discussed our use of CRCs and hash tables to do function comparisons to find identical and equivalent function instances. At the same time, we also had to store intermediate function instances in order to both reduce the number of disk accesses we have and also to reduce the number of phases we apply. So in that DAG I showed, at every point in the DAG, we stored the function instance for that DAG. And so the next time we go, we don't have to reapply all the optimization phases, but only apply one phase to get a new function instance. So also note that the number of function instances that we have to store at any point is never more than the depth of the DAG, which in the worst case was 44. So it's not a big space overhead, but it gives us huge savings in time. And this is something for debugging that we had to maintain logs to restart the search if after a couple of days we find, okay, the system now crashed.
Were you doing breadth first search?
So we did both. So in breadth first search, we have to, so this is, the second point is more true in depth first searches, where we are doing depth first, right? So you go down and then we store all the intermediate function instances for that path.
I see. So you were not storing all the functions seen so far?
No. We only have to store the one along that path. So we go here, so we only apply the optimizations along that path. And once you roll back, you never need the functions after that point.
I see, but what if you have reconvergence in your
Yes, if you have reconvergence, that you would be storing that again. Yes, but we didn't want...
you would be re-exploring that part, right?
Not the entire path. Once we read something which has been seen before, we don't have to follow after that.
How do you know that it has been seen before? You must have stored it, right?
Oh, we store the CRCs for everything.
Yeah, that's what I mean.
Yes.
Okay, got it.
Okay,
So
okay.
you store the hashes for every guy scene.
Yes.
But the actual function only for the guy.
Only
on
for the
steps.
pass. Right. Okay, sorry for that confusion. Okay, so briefly a summary of some of my other work. So I started my research at FSU working on the VISTA system, which stands for VPO Interactive System for Tuning Applications. This provides an interactive, this is an interactive system and provides a new or a different code improvement paradigm in which you can go in by hand and apply the optimization phases interactively. You can select them interactively in any order. You can see the code that has been produced. You can undo certain optimizations. You can see the performance of other optimizations and many other things. So this is very useful as a research tool, as a teaching tool to show the internals of compiler optimizations to students, and it's also very important for debugging, which I use frequently, and it's employed in 3 universities now. So this system has been described in my LCTS and text paper, and this is the main user interface window of Vista, where in the right hand side you can see the control flow blocks and the instructions which are represented in an intermediate language. You can also represent them in assembly language for any machine. And here you can these are the optimization phases that have been applied and the improvements in both code size and instruction count after each optimization phase. And you can undo optimizations, you can traverse the optimizations, each transformation, each deletion instruction of RTLs and everything. And so it's very useful. As part of this work, I also implemented a genetic algorithm to effectively find the effective phase ordering for each function, to find a good phase ordering. So here we were not trying to find the best phase ordering, but only using genetic algorithms to find a good phase ordering. So for that we used genetic algorithms. And during my implementation of genetic algorithms and during the study, I realized that there was actually a lot of redundancy in the space. And then in my next work, I tried to exploit that redundancy. At that point, I actually felt that I was going to use genetic algorithms for most of my dissertation, and so I wanted to make them fast, just to get my work done quickly. So here, we applied a bunch of techniques, mainly categorized into 2 different categories. The first was to avoid redundant executions of the application, and here we applied a bunch of techniques to find dormant phases, to find identical phases, and some of the things that I described earlier. And we found that we can avoid 87% of the executions and reduce the search time by over 62%. So this was one of the inspirations which led to my exhaustive work. The next bunch of techniques was geared towards improving the genetic algorithm itself to find comparable results in fewer generations. And we were able to apply our techniques to reduce the number of generations by over 59% and reduce the search time by a further 35% in addition to the 62% that we had here. So these were very interesting results and published in our PLDI paper in 2004 and in the TACO journal in 2005. So this work was done after I did the work I described in my main part. So now I had all the phase order space information for large number of functions, and so we thought that it would be interesting to see how the heuristic algorithms compare as compared to the optimal phase ordering. This is a study that had never been done before because no one before us had the optimal phase ordering. At the same time, we realized that heuristic search algorithms are still important, since exhaustive phase ordering for some functions can take very long, and for some functions we were not able to get them, like we were not able to get the best phase ordering for 10 functions, right? So heuristic algorithms we thought were still important. So in this study, the main concern was, or the main part was to compare different heuristic algorithms with the optimal phase ordering to both compare their performance as well as their cost, and to see how we can use certain properties of the phase order space, like to improve the algorithms. We also showed the importance of selecting a good sequence length and the importance of leaf function instances to find good performance quickly. So this is what I presented at CGO in March. At the same time, I received an IBM PhD fellowship last year, as part of which I did an internship at TJ Watson in the fall, in which was my first exposure to dynamic compilation. So in that part, I mainly explored sequence compilation and trying to find the drawbacks of background compilation and to see what is the best compilation strategy. So in this case, we demonstrated the shortcomings of the current compilation approach, the background compilation, and described the importance of assigning a minimum compiler utilization for the compiler. At the same time, we also discussed new strategy, and this was also the first work where we saw how we need to adapt the strategy, to modify the strategy, the controller, the compilation strategy, if we move to multiprocessor machines where we now have free cycles. So if we have free cycles, what changes to compiler strategy should be done in a JIT compiler environment. So these are also very interesting results, and they will be published in our VE paper in 2007 at FCRC in June.
So what does the phrase asynchronous dynamic compilation mean?
Okay, so it mainly means that the compiler is a different thread than the application. So they are asynchronous, and the compiler is dynamic, so it's a JIT compiler. It's a just-in-time compiler. So it's done dynamically at runtime, the compilation, and the compiler is actually a different thread from the application.
So, but the thing is that what is the point of this? Why don't you just first compile the code and then run it? Why do you want this separate thread business?
Because it's obviously it's better to have two threads, because now if you move on to a multi-core machine, you can run both of them simultaneously. Also, it's if you
you can start running the application while the compilation of the rest of the application is in progress. Is that what
yes, so yes, that is exactly the case. So many JIT compilers, they can work in two modes. They both have a interpretation mode and a compilation mode. So they start interpreting the function, and at the same time they can also compile some of the other functions. Also, there are different levels in compilation. So the earlier levels like O1, O0, they don't apply all the optimizations or all the time-consuming optimizations. So they can be applied quickly, but they don't have as good a performance improvement. So you can compile at O0. So it's good performance, but not the best you can get. Start compiling or start executing. At the same time, you can then also compile some of the remaining functions.
I see. So later on, when you create a faster version of a particular function,
yes,
then you'll have to do dynamic code replacement somehow.
Yes, you can. Yeah, you have to do that. But it's not only the function that is being compiled that has been executed that you have to compile. You compile some of the remaining functions. Yeah, and you have to do dynamic code insertion and relocation and all that. Yes.
Okay.
So here what they do is something called background compilation, in which there are two different threads, and it's you cannot just compile everything and start running, because then there's overhead of startup and all those things, right? Because then there would be pauses in the application if you wait for everything to get compiled before you can execute. So this is to solve all that.
Is this something that's already in some Java?
What's that?
Some JVM already implements such
The background compilation?
concurrent
Oh yes, most JVMs I saw do that. So they have the compile in a different thread, which is also intuitive, right? Because it migrates easily to multi-core machines, and also it's good from a software engineering point of view, and you don't have to compile everything before you start running.
So what system did you implement this in?
This was most of it was in J9, in IBM's J9 compiler, which is their production version, and I have ported some of these changes to JIX as well, but not everything as yet.
So the compiler you described in your earlier work, the most of your talk, that's a C functions.
Yeah, that's a static C compiler, yes, and this was a Java JIT compiler. Okay, so the final part is some of my future research directions. So my main work has been in compilers, and I regard compiler as a bridge between high-level languages and machine architecture. So in this slide, I wanted to discuss some of the trends that I see happening in my field. So because of this structure that I see, any trends that happen in machine architecture or in languages, they will have a direct effect on compiler technology as well, and future compiler research. So then what are the trends that I see in machine architecture? Obviously, there's a big move, a paradigm shift towards multi-core architectures. And this is mainly because of two reasons. The first is the inability of computer architects to exploit further instruction level parallelism without increasing the complexity of the chip. And the other reason is obviously power becoming a first-class constraint. So there is a great shift towards multi-core machines. And the bad news here is that architects don't really have a very good solution up their sleeve. So they're basically putting off the responsibility both to the compilers and the application developers, saying that we have chip area, but we don't have a very good solution. So if you can find something to do, then we can give you as many cores as you want. So many of the things that I see happening is support for greater performance monitoring, in order to even measure something like bus activity. At the same time, I also see improved software control reconfiguration being provided, in the sense that the compiler or the application can now control different parts of the chip, like shutting down or starting different parts of the chip, or even controlling the data path in the microarchitecture. So the big news here is only that architecture cannot do it alone and has to increasingly rely on both languages and compiler to get performance improvements in the future. On the languages side, there is certainly some of this has affected the languages side as well. So there has to be now greater support for parallelism. This is not a new field and has been studied for some time in the high performance community, getting automatic parallelism. So this was found to be non-trivial to do in many languages like C, which had which has pointers and no type safety and everything. So automatic parallelization in such languages was found to be difficult. However, there are now new research to find new languages or to develop new languages where there would be basic constructs to exploit parallelism to give the user better opportunity to parallelize the application. At the same time, I see there is a greater push towards supporting higher level constructs in languages, like even transaction-based software transaction or garbage collection, exceptions and so on. And this means that in both of these cases means that the compiler now has to find efficient implementations for both the high level constructs as well as the new languages and the new constructs to exploit parallelism. At the same time, I also see a greater support for virtual machines because of their known benefits of portability, isolation and everything. And with virtual machines, there's then a greater need to support dynamic code generation if we want to support portability, which means that the compilation decisions are increasingly pushed closer to the architecture and cannot be made statically. So based on those trends, in the future, one of my main areas I want to work on is enhancing compiler and language implementation. So this includes what I have done in the past, that is improving the performance of generated code by using optimizations. The first is developing new optimizations for some new architectural features that are introduced, or also to use phase interactions to even develop new intermediate languages, to develop new better languages and to also generate better code. At the same time, the faster compilations that I described are important in a static compiler, but they will become much more important as we move to a dynamic compiler. In a JIT environment, faster compilations are what you need. At the same time, in another part, I also want to work on reducing the penalty of providing better implementation of many of the high-level language constructs. Something like type safety or exceptions, garbage collection, providing better implementation so that the productivity of programmers can still be improved by using the high-level constructs, but we still have efficient implementation of them to the machine code. Also at the same time, it's important to provide automatic task decomposition, mapping on different chips, different cores, as well as providing synchronization among the different tasks, so that again you can increase programmer productivity and get good performance as well. The second area which I have explored a little bit is dynamic compilation and virtual machines. So as I said, virtual machines are likely to grow in importance, I feel, and the main reasons are the increased productivity, isolation, interoperability that they provide. And the challenges in dynamic compilation are earlier they were just when, what and how to compile, but now as we move to multi-core architectures, it will also be when, what and how to parallelize the application among the different cores. At the same time, also see the possibility of using hardware performance monitors that will now be present in the architecture in order to improve the performance of compilers in just-in-time compilers. Also using static analysis in combination with the dynamic compilers to produce better code. At the same time, I also think what is needed here are better debugging tools, which are I think lacking in this area in both virtual machines. As you increase the level of abstractions that you now have, both hardware and software, you need debugging tools to do that. Also, as you move to multi-core architectures, multi-core heterogeneous architectures, then debugging tools are certainly not present, and it's an open research area. If you can even have debugging tools without architectural support is an open question. The third area which I would like to work on is heterogeneous multi-core architectures. So this is, I think heterogeneous is important because I think only heterogeneous can provide the best performance, cost and power benefits that is needed. So challenges here are to appropriately schedule the task on the different cores. We want to schedule your most compute intensive task on the most high powered core that you have. allocate resources properly, and to use phases in execution to appropriately remap the task at runtime. It will also become important is dynamic core specific optimizations, because now applications are running on specific cores, and so you would have to do some kind of dynamic optimizations. And many of these heterogeneous architectures also share various structures like caches and memory, and so automatic data layout to prevent conflicts will also be important. So this is something I would like to work in the future, and I'll take your questions if you have any further questions.
So you've done some simplifications in order to make this. It's about the first work you described in detail. So you've done some simplifications to make the size of the space become smaller. Do you know how much each of these simplifications is important for? Or for example, this one that you're only using...
what simplifications are you talking about?
For example, you're only using each optimization once.
No, not really. I'm not using each optimization only once. Each optimization can be active multiple times. The only optimization I have restricted is loop unrolling, which can only apply once for each loop.
So what's the difference between a leaf and a non-leaf? I mean, you could get until the end. If
Yes.
you apply everything,
Yes.
everything will be a leaf in the end, no?
Yes, but there are some instances before the leaf, right? Leaf is not always the optimal. In most cases it is, as I said, for most of the functions. But then there are some optimizations which actually make the code worse. So we maintain all the function instances, not only the leaves. So everything will eventually come to the leaf, but we also have all the other function instances as well. Just because leaves are not always optimal. Otherwise we can just concentrate on the leaves.
Another question about, so you think heterogeneous multi-cores will be better? Kind of, it seems like the management of this is going to be...
Management will be more complicated, but if we can get the management right, then I think it can provide us the best balance of performance and power, as well as cost as well. Best way of utilizing the silicon area.
So does anyone need any compiler for such heterogeneous system?
Yes, I think there is some work going on. I read some work where they are doing this. I don't exactly remember where it was from, but yes, there has certainly been work to do this task assignment and to map different applications on different cores. And I remember the paper, but I don't remember the authors now. Yes, there has been some work done in this area. Yes, and it's important for the cell and such architectures. Yes.
So, to follow up on Russ's, one simplification you made is that each method is standalone. There's no inter-procedural optimization.
Yes.
So while this statement stood for 40 years that you cannot do an exhaustive search of the phase ordering, will that statement still stand if you include inlining and other inter-procedural optimizations?
I'm not sure. We'll have to see. The space will certainly be much more bigger, and it will be much more complicated to do exhaustive reorderings of phases when you also include interprocedural optimizations. But I don't think it's impossible to do. I think it can still be done, but it will be more difficult to do and more challenging to do.
Thank you.
Thank you.